Okay, it looks like we're also picking up another person. Okay, so I've shared my desktop now to see how we can demonstrate the Jupiter lab, or the moons of Jupiter lab. So let me go ahead and open up the program. So it installs it at juplab.exe. Apparently I haven't run it before. Okay. Might as well. Oh, okay. So it's created this new icon here. Okay. Okay, so this is what you should be getting as an opening screen. Then you click File and Login. And I usually just log in with my first initial. Since we're doing the lab without groups or tables, that's, sufficient. Okay. Oh, wait a minute. Oh, Jupiter's, that's not the correct lab. Let me just take a quick peek.
Yeah, that's what I have.
Okay. Yeah, maybe we can do different things with this lab. Well, we don't really want to measure the speed of light. We just want to plot the positions of the moon. I don't know if it's going to do that for us, though. Well, the data taking is the same. So if you click on one of the moons, this identifies the moon as Callisto. And what you write down or what you record would be the position with either east or west. So in this case, it gives us the position 9.2 east. And the units are Jupiter diameters or Jovian diameters. So you would record that. Now, I don't know what the observing, okay, so data interval looks like we're observing every 24 hours. Okay, and then you just go through and click on the moons. If you have a data interval of 24 hours, that's actually pretty long. So you probably want to pick the outer three moons. So in our case, we would have Callisto and see if this is Ganymede. What we're interested in here would be the x-coordinate in Jupiter diameters. The 6.00 W stands for west. I'm not quite sure if it's recording the correct thing, though. Well, let me record a couple of days worth, and then you see what we get. So this is Europa, 3.70 west.
Do I need to be hitting the record button as I go through the days?
Well, it depends. If if you want to use the computer to plot the data, then you want to click the record button after every moon. I'm not sure that this is the correct program, though, because it says Jupiter's moon and the speed of light. Let me just X out of here and oh, okay, here it is. Here's the correct one. Revolution of the Jupiter moon. I had that on my desktop all along.
All right, I think
Sorry
I
about
may
the
have downloaded,
confusion.
because I have up the same one that you just had up, so I think I may have loaded the wrong one.
Oh, okay. So you had with the teal icon.
Yes.
Okay, Jupiter. Yeah, that's Jupiter's moons and the speed of light. Because the speed of light would be measured by how long it takes light to travel across the orbit of one of Jupiter's moons. I haven't run the lab myself, but I think you can probably calculate a value for the speed of light based on each of the orbits, and then maybe take an average. But yeah, we definitely need the other one, the yellow icon with the revolution of Jupiter moon.
Okay.
So yeah, you may want to just go back and download the other one.
Okay. I can do that.
Okay, I'm just logging in right now. It looks very similar. So click File and Run. Okay, and start with today's observation date. Okay, we have a cloudy. Yes?
Okay, I see the cloudy. Yeah, I talked about that in the book.
Yeah.
I did download the revolution of moons of Jupiter, but I got the teal icon, not the yellow. Because I just double checked what I downloaded.
Well, I guess it depends on what it looks like. Well, let's see. Let's go with this. Although I'm thinking right now the data interval is set to be 24 hours, and that's usually only good if we want to observe the moons that take longer to go around Jupiter. So 24 hours is best for Callisto and Ganymede, but when we get to the moons that are closer in with the smaller orbits, Europa and Io, then 24 hours, just taking their position once every 24 hours may not be often enough to get a nice smooth curve. So let's see if we can change that. See timing. Yeah, and change the observation step to 12 hours. Okay, and well, since that would be a cloudy day, we wouldn't put that down as a line of data. So let me open up the lab manual to the Moons of Jupiter lab. Hang on, let's see. I'm just counting the number of entry lines here. Oh, okay. Yeah, this is the new edition. In the previous edition, there is a table for the data, and whenever you have a cloudy day, you record that in a separate table. But this updated edition, maybe people got too confused with keeping track of running dates in two different tables. So I think we went back to just one table. So what you would record on the first date, if you get a cloudy day like this, you would just leave that line blank or make a like a squiggly line through it that on this particular date and time we don't have an observation, we don't have data because it is cloudy. So click on next and you see that, let's see, now we have 12 hours, so this is the second observation on the first date. So the date would still be February 10th, 2012, but instead of 00 for the time, we would have 12 noon.
Okay, yeah, I see that.
Let's see, we see two moons. Let's click on them. Okay, so here we have Callisto at 10.8 east in Jovian diameters. This is the coordinate you would write down for Callisto in the data table. So that would go into the second line, and you would record 10.8 east for Callisto. And then you click record. Oh, okay, so we can actually click on all the moons. See, this is what you want to see for the revolution of the moons of Jupiter. This recording window looks different than the one, we accidentally pulled up for the other moons of Jupiter lab. So this is what it should look like, where you have Io, Europa, Ganymede, and Callisto. And when you click on the moons, it would fill in the correct coordinates. Let's see, let me just click OK.
I see. Okay, yeah, I see that.
Okay. And you have to aim pretty well with the cursor, because if you click anywhere in space, it'll tell you what coordinate that is, but then you don't get the moon, the name of the moon. Okay, so this Ganymede is 7.30 west.
Okay.
So if we go to the record button now, we see it has filled in Ganymede also.
Okay. All right. It
Well,
does
we
seem
know
like
that.
I'm doing it right then.
Oh, okay, good. Yeah, we know that Jupiter has 4 large moons, so we need to maybe zoom in a little bit to see if we can see the other 2. They must be really close to Jupiter, so either passing in front or behind. So let's just zoom in and see what the story is. Well, I can't really see much, so they must both be behind Jupiter. So maybe what we can do is just go to the window here. Oops, it's not centered on moon. Yeah, program is so picky. Let's just go back out. Go back to Ganymede. Let's see if we can just enter 0 here, 0.0 for Io, and 0.0 for, maybe put, I guess 0.0, it doesn't matter if it's east or west. So let's just click OK. Measured value is incorrect for Io. Well,
Could it be in front of Mars or Jupiter? You just can't see it. It blends in.
Yeah, but I think I can only record something if I click on it. Let's see. Oh, okay, so it took it when I put this in the correct format. So 0.00 and then either east or west. It didn't seem to mind that.
Okay, I see. Okay.
Well, if you're just recording 3 moons, then you can go on, once you have the position of the 3 moons that you're doing. You can do all 4 moons, and then I would just give you extra credit for, doing the additional moon. But yeah, I would only require to do 3 moons because, it takes time. Okay, now that we have recorded the 4 moons, we can click on next and see that there they are. They've popped out. And then we just go through again. Callisto. Let me just record a couple of positions here. Let me record a couple of days worth, because then it usually gets confusing again when you have to interpret the data. Okay, so we got all 4. Go to next. Oops. Picky, picky. You can already tell when you click from one day to the next that Callisto seems to hardly move, seems to hang around east forever. And the moons with the smaller orbits, they switch from east to west much quicker. Of course, you want to stop and write down the coordinates for each of the moons before you go on. See, Callisto is still hanging out way in the east.
So I should write down the coordinates in the lab manual as well as record them on the computer? Or can I just do one or the other?
Well, I think the computer will give you the option to print out the data table, but just in case, can't hurt.
Right. Okay.
Okay, so it looks like Ganymede is smack in front or behind behind Jupiter. Well, we can't really tell. I mean, I don't know if it's hiding, being camouflaged by those storms here. So we have to enter 00 for it again. Just so it won't complain. Okay, let's do one more session and then see if we can plot the data. Okay. And you have 2 options to plot the data. You can plot it by hand. If you go to page 7-11 and 7-13 in the lab manual, there are templates for each of the moons. And it's already labeled. The first template would be for Io. And you can see when you look at the position in JD, I think, one direction is positive, the other negative. Doesn't really matter which one you take positive. I think east is positive and west is negative or something like that. But the axis, the y-axis, is already scaled to um, how far away Io can move from Jupiter, and it can't really move any further than 5 Jovian diameters, so it stays within that. And for Europa, you can see that the axis is scaled to 6, positive or negative 6 Jovian diameter at the most. And if you go to Ganymede and Callisto, they're a lot larger because the moons have a much larger orbit. So you don't have to worry about having to scale the y-axis. For the x-axis, you use time in days. So for your first observation, that would be 0, and that would be smack. You could put that smack on the, along the 0 mark at the very left edge, and then the small tick in between would be half a day, so that would be your noon observation, and then the second or the first larger tick, or 2 squares over, would be the next day, so that would be 1, and then you'd have 1.5, 2, 2.5, 3, and so on. This is if you would have 2 observations each day, like we just did. So if you have an observation interval of 12 hours. If you would choose an observation interval...
That makes sense.
Yeah. For example, if you're interested in mapping Io, you would actually want to choose an observation interval of 6 hours because Io moves so fast. So you want to, just in order to catch a lot of points per one orbit of Io, you'd have to shorten the observation time to 6 hours. And then you could use like 0.25 for the first tick mark, and then 0.5 for the next, and 0.75 for the one thereafter, and 1.0. So you could do it that way. Okay, well, let's see what we have for data. Data. Review, edit, print. Yeah, this is the data I have recorded right now. And you see how it uses positive and negative here.
Yeah, I see that.
So if I wanted to go ahead and edit it, I could go ahead and do that. For example, if I hadn't filled in the 0 whenever the moons were smack in front or behind Jupiter, I could go ahead and do that now. And then we have I wonder what this does. Oh, if I have this experiment. If you don't want to use those graphs, those templates that are already pre-printed in the lab manual, then you can, this would be the second option. Then you would use the computer to graph the moons for you. That might be, if you know what you're doing, it'll be a lot quicker and it'll go easier, but you kind of have to get used to what the graphing program means. So it might actually be more instructive to do it by hand.
Okay, that's fine. I can do that.
Yeah. So let's see. Let's just do Europa. And you can see, we haven't taken that much data yet. All moons orbit Jupiter in a very smooth fashion. They just go around Jupiter the way the moon goes around the Earth, the way the Earth goes around the sun, just very smoothly, with a speed that hardly changes, maybe just a little bit because, the orbits are almost circular but not quite. So there are no jerky motions. That means when you connect, you don't want to connect the dots because then that would imply, okay, it moves linear, and then when it gets to that particular data point, it jerks. and suddenly changes its speed and changes its direction very quickly as if it were jerking around, which it is not. So if you plot by hand, you want to make sure that you draw a smooth curve, kind of like a rounded, wavy sine curve through the data points. If you use this computer program, then let's see. You go to plot and fit the sine curve. And then we want to, you sort of have to estimate a little bit what the period already may be, what the amplitude may be. So in order to use this tool, you should have a little bit of an idea of what these terms mean. So amplitude, when you're dealing with a sine wave, means what is the maximum distance away from the zero mark that it can get, either direction. So in this case, it looks like just a little bit over 4. Or actually, in this case, it might nearly be 5. So let's say something like 4.75. And again, wait a minute. That's the wrong field. I would go into the amplitude, 4.75. And again, this is just an initial estimate so that the computer can make an initial fit. And after this initial fit, we can use the slide buttons down here to adjust, to fine-tune it, to make it match exactly our data points. So now we're just giving it a rough estimate to get started. Okay, and the full period means, 1 point. So here we have a zero crossing, and then the moon goes west, swings around, we have another zero crossing, but this is only half a period. So this is kind of like a swing, that started at 0. Someone pushed the person, and the person went forward, and then now the person's coming backward, but it's swinging back all the way, to the largest extension. So the period is not complete until that entire movement is complete. So until the person comes back to the 0 point, moving forward. So for a moon, that would mean, the moon starts, or where we start measuring the position would be catching it right when it passes in front of or behind Jupiter, moving west, all the way as west as it goes, and then it swings back around, crosses this time on the other side of Jupiter, but then it has to complete its eastern extension, before it crosses Jupiter again, going back west. So the full period would be the entire thing. Now, we didn't take enough data to read this off, but we can estimate and saying, okay, we started at 0, and it looks like, if we sort of make a smooth line through here, right around here, that it crosses over, goes away. So from the first 0 crossing to the second 0 crossing would be half a period. Okay, let's just see what the ticks mark mean. I think they're every 2 days. 68, or maybe not every 1 day. Let's see, 68, 69, 10, 11, wait, 68, 69, 70. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it looks like the tick marks are 1 day, which would make sense because we took 2 observations per day. So this was our first observation. This was our second observation on the first day. Then this was our first observation on the second day, second observation on the second day, and so on. Okay, so that means our half period would be about just over 1.5 days. So, let me maybe say 1.6 days. And then T0, okay, mod joule date. Let's just put the 968 here. This is where it has a zero crossing. Okay, so let's see what it does and click OK. Okay, so it gave us a sine curve, and what we need to do now is to actually match that sine curve, and instead of having it squiggle around, not passing through very many data points, we want to get it to move smoothly through the data points. Yeah, we can adjust the sliding buttons here. So here we can adjust the T0, and it looks like we have to adjust it even more, so I'm going to reset it here. If I click this reset button, it just keeps the curve to where we just had it. It just puts the slider back in the middle so that we can move it over further. See, I want to start the 0 point. I want to make that line up. So I'm going to have to unfreeze the slider again. Okay, so now I have my 0 point. But the problem is, you know, when it passes through 0 again, that happens much quicker than is indicated by the data. So that means I have to make the period larger. And so I use the second sliding button here so that I can get the second 0 crossing to coincide with what I think it should be. So I'm going to have to do the same thing and just keep readjusting the slider. Until I get it where I want it to go. Okay, but it looks like the amplitude is a little bit short. So we're almost there. Let me fiddle around with the amplitude a little bit. That's the bottommost sliding bar. Aha, something else happened, of course. Our 0 point has moved again. So I guess you have to sort of play around in such a way that you adjust all three at the same time. Okay. Put that back in the middle. Spread the period out a little bit more. Okay, almost there now. So it just takes a little bit of fiddling around with the sliding buttons. Okay, now that looks like an excellent match. And yeah, with the amplitude, that looks about right. You know, we have so few data points of Europa's orbit. We're not really sure if that is going to be its maximum. Yeah, that's definitely not its maximum. But let's just go with that. I mean, this is close enough. Okay, and then we can read off on the bottom right here what the period is in days, and that's what we would write down also underneath the graph. So the period in days would be 3.575 or just 3.56 if you wanted to round it off after two digits after the decimal point, and then the amplitude would be 4.79. So that would be for Europa. By the way, if you go with the computer option and you're not using the graphs that are already pre-printed in the lab manual, there is a table 2 on page 7-8 where you write down the data. So this is where in days you would write 3.58, actually 3.58 days for Europa, and then the Jovian diameter, the amplitude, would be 4.7. Okay, and then you would go ahead and load the data for the other moons. I guess we can save the plot image. So for those who don't want to work the graph by hand in the lab manual, you probably want to save the plot image. So for me to see, you can just save it wherever you want. Okay, well, we can take a quick look at, see, we did Europa. Let's take a look at Callisto, the one that's furthest away. And you can see Callisto hardly moved at all. So with such a short observation span, we just did like 3 or 4 days, there would be no way to get a good grip on Callisto's orbital period. I mean, we probably got one of the furthest west extensions or east, but that's about it. I mean, we wouldn't be able to do much of a fit for a sine curve here. So for Callisto and also Ganymede, probably you need a lot more days. That's where the 18 lines of data come in.
Okay, that makes sense.
Yeah, so Ganymede we get a little bit more. So we could probably get a quarter of a period, going from one maximum down to the 0 line and then quadrupling that time. But still, for Ganymede, you also need more days to have a nice repetitive sine wave pattern. Okay, let's take a quick look at Io. Io is going to look like that also when you plot the data by hand. And just like, what is it doing? And of course, it's smoothly orbiting Jupiter, but it does so fast that when we observe only once every 12 hours, we don't get very many points in one of its one of its orbital periods. So it just seems to jump around like that, and we would get more points like that. Now, that's what I'm recommending. If you do want to observe the inner 3 moons, that you use an observation interval of 6 hours instead of the 12 or the 24 hours. Then you would get a lot more points for Io within one period, and it would look a little bit smoother.
Okay.
Okay, are there any questions so far?
No, that makes pretty good sense what you're explaining there as far as plotting the data and actually recording the data. I don't think that's going to be too difficult. I should be able to do that fairly quickly.
Okay.
I did have. Go ahead.
Oh, I'm sorry. Go ahead.
Yeah. Number 6 was kind of an odd question.
Okay.
I haven't gotten that far yet, but I saw it, and then I don't know. I haven't really tried to figure that one out yet, so I'm not sure if it's going to be problematic or not.
Well, it shouldn't be, but let me go to the whiteboard. I'm going to end the app share. Okay. Oh, yeah, Nancy. Hi, Nancy. Did you see any of the app share session when we were talking about the Moons of Jupiter program? Yeah, you can also type your answer. You don't have to speak if you don't want to. Yeah, how did you find? Go ahead. Oh, how did you find the graph again? Please, let me check if my Jupyter program is still up. So I think I closed everything. Um, well, how about I talk about how to deal with the data, and then we'll just go back and open it again at the end of the session. Okay, I'm going to switch it over to the whiteboard now. And well, you get from all 4 moons, yeah, let me just write down for Europa. Okay, so we have the moons of Jupiter data, and we'll go by the example of Europa. See, we recorded, let's see, what was it? 3.58. The period was 3.58 Jovian days, and the semi-major axis, or the amplitude, A was, oh, what was it again? 4.79, something like that. I think it was 4.78. Yeah, it's just approximate, so that's fine. And that was in, wait a minute, messed up my units here. In Earth, the period is in Earth days because we do our observation on Earth time. So period is in Earth days, and then the A, 4.78, that was in Jovian diameters. So JD stands for the Jovian diameters. So that was the distance from Jupiter, and the period is measured in Earth days because our observations were done in Earth time. Okay, now when you look at table 2, in order to, before you go ahead and calculate Jupiter's mass, you want to convert the Earth days to years, and you want to convert the Jovian diameters to astronomical units. So, yeah, let's do that. I'm just going to change the pen color. So convert period in days to years. Wait a minute, that was supposed to be blue. Okay, let's see. Okay, so convert period in from days to years. Okay, well, how do you go from days to years? What do you have to do to the 3.58?
Divide by 365.
Exactly, yeah. So we have 3.58 days. Well, I mean, put it in terms of a conversion factor, then you want to go from days to years. So you multiply by a conversion factor where you have the unit in the numerator that you want to wind up with, so 1 year, and you have the unit that you want to cancel out in the denominator, which would be the 365 days. I mean, it's basically what you said. It winds up being dividing by 3.58 days by 365 days per year. So what did you get for that? Do you have a calculator handy?
I do. One sec. .0098.
Okay, so 0.0098?
Yes.
Okay. Okay, the unit would be years now. Okay, let's convert the semi-major axis into, wait, what happened to my D here? Okay, hang on. From Jovian diameters to astronomical units. I'm just going to have to fix my unit up here. For some reason the D went away. I'll have to do. Okay. Well, the conversion factor is that there are 1,050 Jovian diameters in an astronomical unit. So what would we have to do to the 4.78 JD to convert it into AU?
You would, you'd multiply, wouldn't you?
Well, but if you think about the unit, okay, well, let's set it up. So we have A equals to 4.78. That's in JD. And if we now multiply our conversion factor, what is the unit that we want in the numerator? So that we want to replace the JD with. That would be the AU, right?
Yeah.
So, yeah, that means our conversion factor would be 1 AU per 1,050 Jovian diameter. So which is the same as we did for the period. We would wind up dividing by 1,050.
1 AU per 1,050 JD.
Yes. So if you would take 1,050 Jupiters and you line them up side by side, that would span one astronomical unit, which is the distance from the Earth to the Sun.
Okay, I see.
You know, we're going to a larger unit, so that means we want to wind up with a smaller number. It's another way of looking at it.
Okay. Yeah. I see.
Yeah, same thing with the period. Yeah. You know, we had 3 days, are a much smaller fraction of a year.
That equals 0.0046.
Okay. Okay, and that's AU. Okay, so now we can actually go ahead and calculate that. That would be question 3. Actually, what we just did was the data for the table. I'm going to add that up here. Oops, oh man, I meant to do that in green. Oh well, I don't want to go back and change it now. Okay, I'm just going to add data, table 2. Okay, and then we would go to question 3. Jupiter's mass from Europa's orbit using Kepler's third law. Okay, yeah, and Kepler's third law was that when you take the cube of the semi-major axis divided by the square of the period for an orbiting object that is orbiting a certain planet or the sun, then that equals the mass of the object that is being orbited in units of solar masses. Yeah, as long as we use Earth years and astronomical units as the units for the A and the P. Yeah, so let's go ahead and calculate that. I'm going to try to switch my pen color to red. And now we're just going to plug in the values that we get from the data table. I'm trying to put my box here where I can start typing. Okay. So for A, we have the 0.0046. Well, let's not worry about the units for now. Cubed. And we're going to divide that by 0.0098 squared. So what do we wind up with? So if we have 0.0046 cubed divided by 0.0098 squared. Of course, it's a little bit tricky to punch into the calculator, depending on what kind of calculator you have.
Yeah, the calculator I've got is not cooperating. Let me grab my other calculator real quick.
Well, you could do, just calculate the cube of one number and write that down, and then calculate the cube of, the square of the 0.0098, write that down, and then just, enter those by hand.
Yeah, the cube number is not enough, I guess, spots on the calculator to accept the answer when I take 0.0046 and cube it.
Hmm.
Let me try it on the calculator on the computer.
Okay.
All right, the 0.0046 cubed equals 0.00000097. Yeah.
Okay, let's
7
say
zeros.
okay. 1, 2, 3, 4, 5, 6, 7. 7 zeros and then
97.
okay, and then divide that by
1 second. 4 zeros. 882.
okay.
That equals 0.001099.
Okay, so 0.001 and then
Yeah.
what comes after the 1?
099.
Oh, okay. So we could just say 1, 1 since we're keeping it to two significant figures apparently.
Yeah.
That's actually pretty good. Usually the numbers you get are 0.001 or something, so 1 times 10 to the negative 3 or 9 times 10 to the negative 4, which would be 0.0009 something. So that's the typical ballpark. And that's also why you take an average of the 4 or the 3 moons that you're doing, in case one of the fits wasn't as good as the other one. So you have 4 values, and the average then is more accurate than each of the individual values. Okay, so and the units would be solar masses. Okay, so that's about right. Let me save this shot. Okay, well, question 4 is the average. So since we only did 1 moon, we can't really take an average. If you do 3 moons, you would add up your 3 values of the solar masses and divide by 3. If you do 4 moons, then you'd add up the 4 values and divide by 4. See, that's the phone in the background. I'm just going to let that ring. Okay, let's go to question 6. I'm just going to erase everything. Okay, and switch the pen color back to black. Okay, and here you want to convert, how massive is Jupiter and Earth masses? So you want to convert Jupiter's mass from solar masses to Earth masses. And we know that one solar mass is equal to 3.0 times 10 to the negative 6. Wait a minute, that one Earth mass is 3.0. Yeah, let me just. Yeah, hang on just a second. Oops, hang on. All right, I'm back. Yeah, I gotta wrap this up soon. Okay. So the conversion factor is given as 1. Oops. It blocked my. Okay. 1 Earth mass is equal to 3 times 10 to the negative 6 solar masses. Okay, we have Jupiter's mass in solar masses. So Jupiter's mass was equal to 0.0011 solar masses, and we want to get it into Earth masses. So now we need to set up our conversion factor. Yeah, let me just abbreviate that to M Jup for the Jupiter mass, so I can squeeze everything in one line. Okay, so we have our 0.0011 solar masses. I'm going to abbreviate that as SM. Okay, in our conversion factor, we want to replace the solar masses with Earth masses. So that means we want to put the unit of Earth masses in the numerator and then divide by the number in solar masses. So 3 times 10 to the negative 6 solar masses. So essentially, we're dividing 0.0011 by 3 times 10 to the negative 6. But actually, that's, since we have a negative exponent, negative makes it positive. So that would actually mean we would multiply 0.0011 by 3 times 10 to the positive 6. But you can do it either way. Not that it gets too confusing.
No, that makes sense. I think I've got it.
So you're getting something like 330?
The 3 times 10 to the negative 6 is 4 zeros and then 3. 0.00003.
Well, yeah, it would be 5 zeros and then a 3.
Okay, yeah. And then that gets divided by the 0.0011, correct?
Well, you want to divide the 0.0011 by 3 times 10 to the negative 6. Or, yeah, what you could do is just divide the 0.0011 by 3 and then multiply that by 10 to the positive 6.
Okay. When you do it that way, you get 0.00367 or 37 times 3 times 10 to the negative 6.
Well, if you flip the negative 6 into the numerator, then it will become positive.
Okay,
Let
I
me
see.
just, yeah, let's just go ahead and divide 0.0011 by 3. You see what we get.
0.00.
Okay, so yeah, so that would be, yeah, I'm getting 3.7 times 10 to the negative 4. Okay, and that we would then multiply by times 10 to the positive 6 if we flip that up into the numerator.
Okay.
Of course, you know, if you have a good calculator, you could enter the whole thing just using parentheses and you wouldn't have to take those intermediate steps. Okay, so we have 3.7 then times 10 to the 2. I'm basically showing how it is done without using a complicated calculator. Just, you know, the simple calculator on my computer. And that would be in Earth masses.
Okay, that makes sense.
And essentially it turns out to be 370 Earth masses. Overall, that's a little bit much, but, you know, we only considered one moon and we only observed for 3 days. So there's lots of error in that.
Okay.
That makes sense. Put that in a note. You know, we only observed one moon for only 3 days. So this value is not very accurate. I mean, that's why you observe 3 or 4 moons over 18 days or 18 observation lines. You'll get a much better result. Okay, well, actually, I'm going to have to jump off now because a friend of my son's is leaving. I'll post these slides in the lab itself and also on the discussion board, and I'll get back with Nancy about, you know, the graph that she was wondering about. All right?
Okay. Thank you for your time. Sorry to keep you so late.
Oh, no problem. Yeah, okay, well, see you next time.
All right,
Have a
bye-bye.
good weekend. Okay, bye.
You too. Bye-bye.